We're going to go through two parts of this valve design exercise. In the first part, we have a valve with a pump, and we're going to be characterizing the performance of the valve either with an equal percentage or a linear valve. In the second part, we're going to just install this valve into the system where we have the pump again and the valve, but now we have a pressure drop due to the system. So we need to model that and see how the valve is going to perform once it's installed. This one would be like if you installed this just on a benchtop, just to characterize the valve, and then the other one is when it's in service. So the very first thing that we're going to need with the valve design is this equation. Now again, recall that CV is kind of like the size of my valve. If I have a very large CV, then I have a larger valve. And the F of L, that's the lift function. So this is going to be different for either a linear or for an equal percentage valve. Now, basically the lift function just kind of depends on the type of plunger that you have in the valve, where it seats down into the valve to block the flow. And depending on the style of this, okay, you can put different trim in here, and that's going to change the, as it flows through here, it's going to change the type of equation that you can use. This is going to be an equal percentage, and this is our linear one. So we want to see which one's going to work best for us. We determine which one's best by how it performs from a flow versus lift. Now, the objective of this is that we want to ultimately have something installed that gives us a very linear relationship between the lift and the flow. And we'll see that sometimes we have to use an equal percentage valve to achieve that in the process, even though a linear valve would be linear without the process. Okay, so let's get into this a little bit more, and we'll do a little bit with Python to show the response of the valve. So the very first one is we want to characterize this, and if you want to come and follow along with some of the, this is the course website. Come to assignments. So just type in that address right there, come to assignments, and we are doing the valve. Okay, valve principles. Okay, you can see a lecture here of some of the design principles from the valve, and lift to flow relationships and how we design valves. And then we have the second one, which is one we're working on right now, which is the valve design exercise, and it's these two parts right here. If you do need to come here and look at the solution, you can do that. There's solutions for part 1 and also for part 2. So if you're getting stuck, go ahead and use those, but try to do it on your own. Struggle with it first so that you'll learn. Okay, so let's just go ahead and code up this function right here. We need to come up with a plot of the flow versus lift. So if I come to Python, I'm going to first of all go ahead and use NumPy, and I'll use matplotlib as well. And I want to have two different functions for the different valve trim types. I need to have my linear function first of all. This one's just going to be a function of the lift. I'll say that x is the lift in this case, and I'll just return x. So if I have x as an input argument, it's just going to return x. And then here's my equal percentage. Now in this case I can choose an R. Typically R is between 20 to 50 for different types of equal percentage valves. And I'm just going to return R to the x minus 1. Let me make this just a little bit bigger because it looks like I'm starting to wrap there on my text. Okay, and now I'm going to create 50 equally spaced points between 0 and 1 just with the linspace. So I want to just plot these two functions, and I'm going to create a new figure, and this is going to be the valve performance when it's not installed in the system, it's just on the benchtop. And then I have my first subplot. In the first subplot, I'm going to have just the function that's the linear function, so lift versus this linear function, and lift versus this equal percentage function, just so we can see what the functions look like versus lift. And then I'm going to have my Y label there and my legend. In my second subplot, this is going to be I'm going to define this Q of X, and this is going to be my flow now. So this is not just my lift versus that lift function, but now I'm going to do the flow versus lift. So I'm going to put in these input arguments here, and I'm going to return this equation that I showed. Okay, this is the equation that we're looking at right here. Okay, so I'll just leave that off to the side so we can see it. And so I'm just programming that in with all of these inputs. Now here's our intrinsic valve performance. Okay, so no process equipment, all pressure drop is across the valve. And here we have our delta P is 100, that's provided by the pump. Now in some cases the pump, if you have more flow, the pump pressure is going to go down, but this is just an ideal pump that always delivers 100 in terms of the pressure. Okay, now here we have our CV. This is our valve sizing, and if that's larger, you have a larger valve. If smaller valve. Okay, here's our linear. This is our flow for our linear function. Okay, and this is going to be just this FLin. I substituted in FLin, and then here's FEP, or equal percentage. So that's the only difference between these two, is I'm just using different functions here for the lift function. And then I have my subplot 2, and this is going to be lift versus flow for the linear and equal percentage. Now again, I'm just using this lin space between 0 and 1 for lift, and then I'm just going to add some things just to make the plot more readable. Okay, so there's our first one. If we run this one, let me just bring this up, and I'll run it with Python. Okay, so the first thing that we see here is, well, let me go ahead and save it, and I'll put it into, so I can write on it. Okay, and bring it back here. And copy it as well. Okay, so I'll copy it into there just so I can look at it. And copy. Okay, and I'll paste it back in. Okay, and then let's just look at what this is doing. Okay, so here is our first function right here, which is just the this f of L equals L. That's our linear one, and of course that's going to give a line. And then this one is f of L equals, and then we have R to the L minus 1. Okay, let me just check that. Okay, so here is those lift functions. Okay, and in this case, R is between 20 to 50, depending on the type of trim that we have. Okay, now when we install this with a pump, okay, this is just our lift right here. This is just the correlation that we had where we have flow equals CV times F of L, one of those two different types of lift functions, and this is the delta P across the valve over the specific gravity. Now in this case, we just have the pump going to a valve like this, and it's just recirculating around. So we know that the delta P across the pump is going to be equal to the delta P across the valve. We're just assuming that there's negligible pressure loss here, so that those two are equal. So I'm just using delta P across the pump right here and using different lift functions there. Okay, so that's the first problem. Just wanted to see, how this behaves, flow versus lift, for not installed in the process. You can see that if you're desiring something that's linear, okay, a linear correlation between lift and flow, that in this case a linear valve is going to work better. So why would we want to use an equal percentage valve? Okay, so the next part of this is going to help us see why we might want an equal percentage valve for our installed process. So now what we're going to do is we're going to add this system. So the system is there now, and instead of just recirculating back to the pump directly, like we did before, we're going to travel through this system that's going to have a certain pressure loss versus flow correlation. In this case, we're going to have this pressure loss correlation right here. The system is going to be, the pressure loss across the system is going to be proportional to the flow rate squared. In this case, it's 2 times the flow rate squared. This is very typical for processes that have a squared, quadratic dependence on the flow rate for the pressure drop. Okay, so what we want to do now is, this is going to be very similar to the last one, but now our pressure drop correlation is just going to change a little bit. Okay, we just want to start off with, as we derive this, okay, our delta pressure, and this is from the pump, is now going to be dissipated not just across the valve, but it's going to also be dissipated by the system. Okay, and that's what I call this one, delta P system. Okay, and then we know that the delta P across the pump is just going to be equal to 100. I've just left the units off here, but you could add those in if it's like PSI or bar or something like that. Okay, and then the delta pressure across the valve, we need to come up with a correlation for that. And so we're going to use our valve design equation. Okay, and here we have our valve design equation, but we just need to solve for delta P V. And we'll just rearrange that, just algebra here. And that is Q divided by CV F of L squared. Okay, so I've just rearranged this equation into that one. And then the delta pressure drop across the system, we were given that as 2 times Q squared. So now we can just plug all of these individual elements into this equation. And that's going to give me this combined equation, which is going to be 100 equals GS, a specific gravity, divided by Q times CV. There's my lift function. And then I'm going to add 2Q squared. So now if I want to use this to come up with a plot of lift versus flow, I'm just going to need to rearrange it a little bit. So just multiplying through, rearranging, again, this is algebra. I'm just going to have my Q as a function of lift is going to be equal to the square root of 100 times CV times F of L squared, okay, divided by, and then this is going to be GS, the specific gravity, 2 times CV F of L. Okay, and this squared just goes right here, not on the outside of those parentheses. Okay, so I have this function right here that I just basically need to plot. And so what I'm going to do is just come up with my lift. Again, I'm going to just say 0, 0.01, 0.02, all the way up to 1. Okay, that'd be 101 different points, or 50, or whatever to show this. Okay, and then I'm just going to calculate my Q values that correspond to each of these, and then just include this on a plot. So let's get back to the Python now. We'll again use NumPy and Matplotlib. I'm just going to go a little bit fast through this first part because we've already covered it. Just inputting some of the data. There's our lift from 0 to 1. And I'm going to have my linear function and my equal percentage function. Now here's my installed valve performance. And this is this equation that we just derived right here. I'll leave this off to the side so we can see it as we're typing in. And so we have just a constant there. Here's our pressure drop across the system. And then we also have this is our process equipment flow with the 100, in this case I put in bar there for the pressure units. Okay, now here is my correlation. Okay, that I had just derived. Okay, and the dP dt, or the delta pressure drop, is going to be 100, and so you can see that's dpt there. Okay, now we have my process equipment plus valve performance. Here's my linear flow and my equal percentage. Now I'm going to plot these, and this will be my valve performance that's installed. I'll do my first subplot. That's just going to be my linear flow, equal percentage flow versus lift. And then I'm going to set some, I'm just going to plot the desired profile. I'll just put a linear profile here. It's actually going to be dependent. We just want to make it as linear as possible. Okay, and then I'll have a legend. And my second one, I'm going to put just the pressure drop. Now in this case, it's going to be the linear valve and the process equipment. Okay, now here's my pressure drop for my equal percentage valve and my process equipment. So we're going to be able to look at these two subplots, or the lower subplots, and see how the linear valve, where the pressure is dissipating with different lift, and also for the equal percentage valve as well. Okay, so here is my plot. Let me go ahead and run this. Okay, and I'll go ahead and do valve 2. And when I run this, I'll see this plot profile. I'll go ahead and save this again, just so I can be able to write on it. Okay, here it is, and I'll copy it in, and then we'll take a closer look at this. Yes, there's a lot of really interesting things going on with this one. First of all, we have our desired profile, which is here in the in the black. Okay, and the interesting thing is now the equal percentage valve is more linear. So you can see that here with the red line. And the linear valve, as you increase the lift maybe to like 20%, you have a very rapid rise in the flow. And then in this region further on, it levels off. So you have kind of two slopes here, a very rapid rise at the beginning, and then it becomes very insensitive at the end. So this is not desirable, because then when we're designing a control system, we'll have different gains in different regions. And so the equal percentage valve is going to maybe perform better for our control system, because then we know that a certain fraction of opening on the lift is going to lead to a certain constant fraction of increased or decreased flow. So let's also take a look at these pressure drops that are happening. So we have the total pressure that's provided by the pump. That's 100. And we'll see that these two, wherever you look at these 2 points, that's always going to add up to 100. So right here it's 50% each. And right here it's 50% each as well. And you can see that the linear valve, this one, the pressure drop across the linear valve goes down much steeper right in this region, leading to an increase in flow. So it's just dependent on the type of trim that's in the valve that leads to this linear versus equal percentage type. So this is a more desirable characteristic, okay, that as we increase the lift, we have a slower decrease in the pressure, leading to an overall more linear profile in the lift versus flow. Let me open up a, there's also an IPython notebook that's available for you to look at to explore some of this. And I'll just go ahead and open up this. This is a widget that I programmed. It lets you vary some of these parameters like the R value or the CV. So let's say we have a desired profile and we want to try to match that black line there. So I might need a bigger valve. Okay, so I'm just going to increase the size of the valve until I can get something that's going to have more of a profile that's closer. But then I see that my R value isn't necessarily, I can adjust that one as well to try to make this a more linear profile. So this is that valve coefficient. Maybe I need to increase this just a little bit more. Okay, that actually looks pretty good right there. So this isn't, it doesn't meet right at the top, but you can see down in this region you have a very linear profile, and then it becomes insensitive. It just can't open wide enough. There's just some system limitations. When you get to really high flow rates, you have a lot of pressure drop from the system, so you really can't achieve that maximum flow rate that you want, even with a large valve. Okay, so I'm just going to increase that, and you can see that you're not ever able to reach that maximum flow rate. And there you can see the pressure drop of the linear valve. Now again, this one falls too steeply right at the beginning, and there you can see the equal percentage valve. So when it's installed, even though if we come back here, kind of a main point of this is that uninstalled, it looks like the equal percentage valve is going to be not as good, but when you install it with the system, especially with the square root dependency and relationship between the flow versus the pressure, that the installed characteristics actually end up being much more linear. So that's very desirable to have a more linear lift versus flow response.